I think if we kick off now then. So thank you very much for coming, everyone. My name is Dr. Di Lewis. I'm the Senior Academic Engagement Manager for the Offshore Renewable Energy Catapult. So I manage ORE Catapult's academic engagement programme, and within that sits the research hubs. And for the last couple of years, I've actually been managing the Powertrains Research Hub from the Catapult end. Today, we will be presenting projects that have been undertaken within the Powertrains Research Hub, with the first session this morning covering the mechanical engineering projects and a session starting at 1 p.m. covering the electrical engineering projects. So a quick run through the agenda. We will initially have an introduction to ORE Catapult from myself, followed by introductions from the programme technical leads from the Catapult and then from the University of Sheffield, followed by the technical presentations and a short Q&A at the end. In some cases, we'll have the students presenting their own work, and in others, where the project is finished or the student is unavailable, the supervisor will give an overview of the project on their behalf. We'll aim to close the session by midday to give those attending both sessions enough time to get some lunch. So firstly, a brief intro into the ORE Catapult. Our vision is to enable innovation and accelerate the development of offshore renewable energy, growing businesses and creating jobs throughout the UK. We have world-leading facilities, research and engineering capabilities, and it is our aim to reduce the cost and risk in the renewable sector in order to grow the industry in the UK. We are part of the Catapult network. The Catapults were established by the UK government in areas of strategic importance to the UK economy, with the aim to develop our capabilities in becoming world-leading in these particular sectors. The Catapult network supports businesses in transforming their great ideas into valuable products and services, delivering impact across the UK economy, enabling businesses to thrive in global markets. There are 9 catapults in total, including Energy Systems, the Digital Catapult, High Value Manufacturing, as well as ourselves. Within ORE Catapult, we are now at approximately 320 employees, following a rapid growth as we support the broad UK renewable sector and all its evolving challenges. We have offices throughout UK, in Aberdeen to support the transition from oil and gas, in Blyth, where we have our large testing facilities, in Fife, Glasgow, Hale, and the Humber, which is really important O&M base, and Lowestoft and Pembroke Dock. As can be seen, we also have bases established within a number of universities through our Research Hub programme. The Research Hubs are part of our larger academic engagement programme and were set up in areas of strategic importance to support the development of the wind industry in the UK. The overall aims of the Research Hubs are cost reductions in CapEx, cost reductions in OpEx, increased energy yield and reduced environmental impact. The Windblade Research Hub with the University of Bristol focuses on developing more efficient and sustainable wind turbine blades. The Electrical Infrastructure Research Hub with the Universities of Strathclyde and Manchester focuses on developing electrical infrastructure required to support the transition to renewables. And the Powertrains Research Hub with the Universities of Sheffield and Warwick focuses on development of larger, more efficient wind turbine powertrains. There are a number of motivations for us in developing the Powertrains Research Hub, all based around improving reliability and affordability of wind turbine powertrains as they get larger and larger in order to meet our 2050 net zero targets. We've worked with a range of stakeholders and aim to disseminate the research to as broad an audience as possible throughout industry and academia. Since its inception, we've developed a strong collaboration with the Universities of Sheffield, Warwick, Strathclyde, Northumbria, and have also undertaken a number of research projects with GE through the programme. We've undertaken a large number of co-funded PhDs and research projects and have disseminated the work at many international conferences and within a number of journals. I will now hand over to Hyunju Lee, our head of turbine systems, who's going to speak to you about how the work has been supported by us, or how the work has supported us.
Thank you. Thank you very much, Dai. Yeah. So good morning, everyone. Yeah, thank you very much for joining this webinar. I'm Hyunju Lee, head of turbine system team at Offshore Renewable Energy Catapult, and one of the industrial supervisor for Powertrain Research Hub program. At World Catapult, our mission is to advance the UK offshore renewable energy sector by enhancing our validation service to mitigate the risk associated with the innovative product, as well as to support the development of new technology. So next page, Dai, please. So today, I'm excited to share our achievement through the Powertrain Research Hub program with a special focus on the mechanical component related project. Okay, next page. Yeah, as my colleague Dai mentioned earlier, World Catapult operates 3 research hub programs and collaborate with over 250 universities. We are also continuously expanding our industrial network. By leveraging this robust network and innovative ideas from universities, we aim to tackle challenges in the offshore renewable energy sector. In essence, the World Catapult with Research Hub, we are bridging the gap between the industry and the academia. Okay, next page. So as you can see, the innovation chain is divided into the 3 stages. The main, first one is knowledge development, which we expect at the university, the research hub conduct, and the second is the technology development and the business development as a final. So the World Catapult, after the universities develop this knowledge and the idea from TRL. So we work together with the industry and academia to bring those TRL to the let's say the ready to be commercialized. So World Catapult play a pivotal role in this chain, bridging the gap between the academia and industry, and the university play key roles to initiate innovative knowledge to address industrial issue. In Powertrain Research Hub, with over 2.4 million pound in funding, we focus on reliability improvement, health condition monitoring, and next generation component development. Okay, next page. Sorry, I did. Yeah, so this is the summary of our role, key role, and could you go to the next page, please? Yeah, over the past 5 years, more than 21 project idea related to the mechanical component has been discussed and registered. And among them, today, we will present 5 key achievements that align perfectly with the Powertrain Research Hub's 3 main goals. Dr. Alex Press studied about the multi-scale wear testing and the simulation of wind turbine pitch bearing. And one of the exciting topics is the technological impact of time-varying wind turbine main bearing loading that will be presented by Mr. Elisha Di Mello. I believe Elisha will become a doctor within a few months from now. And Dr. Gary Nicholas investigated 2 interesting topics. The first one is the evaluation and the monitoring of bolt tightness on wind turbine drivetrain component. And the other one is the oil film sensor for hydrodynamic bearings. PhD student Ms. Emily Priest will present her ongoing research about the facing material for hydrodynamic main bearings. Okay, next page, please. So thank you once again for your attention, and let's work together to bring technology to the market faster. I'll hand it over to Professor Rob Dwyer Joyce.
Thanks, Hyunju, and good morning, everybody. As Hyunju said, my name's Rob Dwyer-Joyce, and I'm director of the Leonardo Center for Tribology. Di, could you have the next slide? So the PTRH is a combination of activities with mechanical engineering and electrical engineering at the University of Sheffield. The mechanical stuff kind of falls in the regime of the Leonardo Tribology Center. And we do all sorts of research and development in tribology, fundamental science to industrial applications and impact. And we're one of the leading tribology groups in the UK. What makes us different is we have excellent experimental facilities, right from benchtop tribometers, specimen to component level. We cover all aspects of tribology in all industrial sectors. We're only talking about wind today, of course, and probably about a third of our activity is on wind. We have some advanced sensing technologies that you'll hear about today. And we also do not just research, but we teach public engagement, outreach, consultancy, and other things. Di, the next slide, please. There are 7 academics in the group. It'll be myself and we that you'll hear from today, because we're the ones that do most of the work in the wind domain. But my colleagues also work in railway, aerospace, manufacturing, tribochemistry, surface treatments, and also bio and human interactions. We're a growing group. The last 2 people on the photograph there, Kate and Tahid, have just joined us very recently. So we've been recruiting actively in the tribology domain. There's a bullet point missing from that. I think it's hidden by the photographs. We've got around about 20 RAs and about 50 PhD students, and that makes us one of the biggest tribology groups probably in the world, actually. Okay, next slide. Our research is based in 4 laboratories. We have what we call the Leonardo Lab, which is what you can see that photograph there, which has got pretty much every benchtop tribometer you can think of. Any 2 ways you want to rub 2 bits of metals or polymers together, we can do it in that lab in any different configuration for testing materials, lubricants, and so on. We have what we call the Swift Lab, which is a heavy component test lab. We've got a wind turbine bearing in there, a small one, and other sorts of apparatus to do larger scale testing. We have a triboacoustics lab where we're building different sorts of sensors. And importantly, we have our own sort of surface analysis and metrology lab where we can inspect surfaces and measure for wear and damage and roughness and so on. Next slide. I broadly divided our capabilities into 4 areas. So we do experimental studies on the fundamentals of friction and wear using generic wear testers, tribometers to look at friction and wear properties, trying to understand more about tribological processes at a fundamental level. And then we work on machine elements of all sorts in all sorts of industries, and that's generally about doing experimental measurements on simulation, on bespoke built test rigs for those particular elements. We build design tools for tribology to help predict wear rates, predict lubricant film formation. We can't yet predict friction, nobody can do that, but we have a go, and looking at surface roughness and contact. And then lastly, you'll hear a bit about today, sensors for tribology. One thing that's unique to my group is the measurement of oil film thickness and other things using ultrasound. The next slide. So Hyunju already went through this list of projects, so I won't dwell on this. You'll hear from some of these people. But what I will do is show you something rather important about the PTRH, which is the next slide. And the PTRH, when it boils down to it, it's a group of PhD students and researchers who are have had the opportunity through the PTRH and working with our partners, OREC, to do some really exciting projects in the wind domain. And there's some pictures of our PhD students at work. You'll hear from a couple of those today. And actually other PhD students around the patch at Sheffield are rather jealous of these guys, because they're doing really, and how many PhD students get to go up a wind turbine during their projects, and 2 of ours have, and they're all working on really live industrial projects. So I'm going to finish with that picture of some very happy, contented PhD students, some of whom have got their doctorates, and some of them will get them soon. Okay, thanks. Now I'll hand over there to my colleague, Professor Wee Long, and she'll give the first technical talk from the projects that have come out of the PTRH. Thanks. Over to you, Wee.
Thank you, Rob. Diane, would you
sorry.
allow me to share?
Sorry, can I just jump in quickly and say if there are any questions, can we put them in the chat and we'll try and get to them at the end? And if we don't get to everything today, we can follow up afterwards. Sorry, Wee. Go ahead.
If you allow me to share. Hi, good morning. So I'm Hui Long. I'm professor in the Department of Mechanical Engineering in Sheffield. And so today I will give you a brief introduction of one of the projects I lead. So this is multi-scale well testing and simulation of wind turbine blades pitch bearings. Some background of this project. So blade pitch bearings are critical component to wind turbine operations. So with the size of wind turbines going bigger and bigger, so blades of those wind turbines has individual pitch controls. So those cause the oscillations of very small amplitude. So under large bending movement, so as you can see some illustrations here. So this resulted varying loading and also very large number of load cycles. Some of those loads will cause the changes of conduct angle of loading elements to the raceways. So cause stress concentration and edge conduct. So that may cause some of critical bearing failures. So one of those critical damages is surface wear. So like force burning and fronting corrosion. So some of the damaged bearing raceway stations can be seen here. However, pitch bearings also have other type of failure modes, such as rolling conduct fatigue. In this project, I'm going to introduce you today is about the surface wear, so force burning and fronting corrosion. So in this research hub framework, we have two projects in this area. So M7A, M7B. So I'm going to talk to you briefly about those two projects. So objective of this project is to develop enhanced test strategy for large scale tests by developing small scale laboratory scale test method, because large scale, full scale testing are very expensive. So we want to understand the frictional behavior and wear damage accumulation using smaller scales before we conduct large scale testing. We also develop finite element simulation models to model wear accumulation to those tests. And so those findings will help us to develop a better understanding for future tests. So work I presented today have been done by those researchers. So have Inadio, Alex, and Zitao. I think Zitao is in audience today. So thank them for their work. So I will briefly mention project M7A. So project M7A focused on understand load distribution caused by the loading of the blades. So this modeled a double roll ball bearing and how the stiffness of supporting plates in the hub and in the bearing affect the load distribution. So by model those load distribution, we can understand. So how can we enhance the stiffness of those supporting plates? So therefore we can reduce the peak load, and therefore to reduce the possibility of stress concentration and the edge conduct of the ball with in contact with raceway. With those understanding, then we further move on to develop the experiments. So M7B is look at those experiments. So we have two small scale and medium scale experiments. So those are developed and performed at the University of Sheffield. So those will support future large scale experiments. So that will be done in the cuttables in the future. So first thing we need to do is to develop experiment test conditions by mapping onto the design of large reference wind turbine. So two important parameters we need to decide is conduct pressure and the sliding ratio. So there are some illustrations here. So what we try to mapping with the large ones, so we make sure what we test in the smaller scale, small scale, medium scale, can mapping the similar operation conditions of the large wind turbine operation. So this is a small scale experiment, design, testing, and finite element modeling. So the tests are performed on a small, test machine. So that's UMT3, and the specimen are cut for a commercial available wind turbine. So the commercial available ball bearings. So therefore, we can achieve the parameters we need, because this is the cheapest way we can manufacture specimen. So this table shows all the tests conducted and some examples of measurements and the comparison between FEA and measured wear depths. So the measured average frictional coefficients is quite low. So we use Alicona to measure the wear depths. However, because the limitations of this small rig, so we are not able to capture the effect of higher oscillation amplitude and higher conduct pressure. As you can see, conduct pressure and amplitude is relatively small. However, this method is very efficient to get wear rate. So wear rate measured is shown here. So this is an essential parameter we need for finite element modeling. So we move on to look on medium scale experiment design of test. This rig is a bioaxial rig. So this is in our mechanical lab. So use this lab, we can move on to look at the bore diameter of 25 millimeters. So we developed this test plan. As you can see, we achieved, we can determine average friction coefficient by use the force measured by the rig. As we can see, the friction coefficient is higher than the small scale test. We believe because this rig design involve other conduct surfaces and also more complex bore movement, as you can see. So the bore shows more complex movement. So this maybe contribute to the higher coefficient of friction. We use the grease lubricant, so that's commercially available, the only one we found for wind turbine applications. So then some measurement and show here. So we measured some of the specimens, and then again we decided we can decide the wear rate from the test. So as you can see, this wear rate, as I mentioned, is essential for the finite element modeling, is higher than the small test. So again, one of the reasons because more complex bore movement, and also because the specimen, the initial surface roughness in those medium scale tests is higher than the small tests. As you can see, those measurements shows some of the characteristics we saw from the measurement from the real pitch bearing sections we studied. So I move on to look at finite element modeling and validation. So this shows FEA modeled wear pattern, and this shows the measured wear pattern, and this is a comparison of the measured and FEA modeled. So green is measured and blue is FEA modeled. So as you can see, the FEA, this in purple color, can show the 3D dimension of the wear pattern, which is quite difficult through the measurements. That means we have to measure all the sections of the wear specimen in order to obtain them. However, we found finite element model overestimate wear depths in all cases. Through the evaluation of the effect of wear rate values, so that means if we consider 100% or 20% or 10% of the dissipated energy to contribute to wear, we are able to find a close match between FEA and experiment measurement. So another important observation is, so when you see this is a conduct stress distribution pattern and also the wear pattern. So we see, so the wear also significant in this diagram will be in the top and the bottom regions where the conduct pressure is not highest. This is because it's the hazer cord slab. So these two images show when the ball is moving over the raceway surface, how the slab regime and the stick regime varies. So you can see, so the green areas are slab regime. So because the higher slab, micro slab regime, so they contribute to greater wear in those regime, as shown in this FEA results. You can also see a line here with smaller wear depths. This is because in those regions we have a pure loading. So FEA provides some a good insight into the more complex condition of both effects of conduct pressure and sliding. So currently we are working on the FEA simulation of large scale test. So, so this is only a very initial preliminary results for a very small cycles of 2000s. So some main conclusions is that, so the measured wear rate shows a similar linear trend. So basically they increase with load cycles. And medium scale test reveal more complex ball movement than small scale, which couldn't produce. FEA modeling and the test from the medium scale shows similar wear patterns. And that's also confirmed conduct pressure, oscillation amplitude, and the hazer cord slip are important to wear accumulation. And we also show FEA modeling can be clearly show the effect of hazer cord slip. And also we can use the evaluation of dissipated energy contributions to wear. In our case, 10 to 20% enabled the accurate simulation. And we currently continue the large scale FEA simulation. And we will report to you our progress in the future. Thank you.
And next we have Elisha. Want to share?
Of course. 2 seconds. Is that all visible?
Perfect, thank you.
Okay, fantastic. So yep, so I'll just crack on then. So this is the my bit of an overview for my project and the work I've done here and with Auric for the last few years. So I'm looking at the main bearing of a wind turbine. Sort of my work is mainly focused on spherical roller bearings that are quite common. Main bearings and wind turbines. The sort of role of a main bearing is to support and react against sort of damaging loads that may be, and prevent them being transmitted further up the drivetrain to critical components like the gearbox and the generator. Failure rates are currently very high. That's problematic as replacement of main bearings is typically very expensive, especially with offshore turbines, because it involves additional factors such as vessels and unplanned downtime for extended periods. And to really understand why the main bearing fails so frequently, we really need to understand the unique conditions the main bearing experiences. So I'm just going to talk to you about that for a slide. So when we talk about the unique conditions the main bearing experiences compared to more general bearings, they experience very low speeds, sort of 20 RPM or so, and exceptionally high loads, sort of thousands of kilonewtons. And there are also multiple combined effects due to the nature of the wind and the wind turbine's adaptive sort of control system. These are just a few of them listed here, but what we find actually is when we consider these as a whole, we find that the loads that are exhibited on the bearing from the shaft are sort of circularly looping, sort of 1 to 2 second duration loads that fluctuate and move around the sort of circumference of the shaft. So this is a polar plot here. So here is sort of an angle, and we're getting these loads that are like looping around circumferential locations of the bearing. So they're very complex loading patterns we're seeing. And so my project really was to investigate the effect of these loading patterns on the main bearing. And so I'm located here. If we're looking along the drivetrain of a wind turbine, and my project is basically split into a theoretical component and an experimental component. Experimentally, the plan is I'm designing a rig and implementing a rig where we can use actuators to load these to create a vector of a load that can then sort of span and move around the circumference of the bearing and give you the same sort of looping loads we've just seen. Theoretically, I'm using a computational techniques to actually investigate the specific dynamics of the rollers, so the rollers, these individual rollers, as they move around the bearing, and how these and input those loads that I just showed you in the sort of page before, the time varying loads. So just one of the initial sort of bits of work I did was this macro slip model that took sort of the first year or so. And the idea was this was a sort of a Newtonian model, so it sort of considered sort of forces and that each roller sort of experienced, such as reaction forces due to sort of the contact, and gravity, centrifugal forces, cage reaction forces, and the like. And it uses these forces to integrate the velocities of the rollers and treat them as rigid bodies. And the idea is that when you have a contact patch is formed due to deformation of material. And when the raceway and the rollers move, if the forces are great enough and friction is not sufficient enough to drive the system, you will get relative differences in the velocities of the raceways and the rollers, creating slip. And this slip is believed to be damaging, and effectively we use frictional energy as a damage metric that's an integral of slip and attractive force in parallel to that direction. So this model directly investigated slip, and it found that when we investigated this sort of frictional energy, these are sort of normalized results here, that we got sort of higher frictional energies, actually lower wind speeds. And this was this actually corresponded to the operational thrust strategy of the turbine, as the turbine started to pitch its blades after that, and we got a higher radial force and less thrust force. So that was an initial result of that study. So that was a macro slip model, and basically the macro slip that assumes that the entire contact patch slips at the same speed. However, this actually isn't entirely accurate, and there's multiple things really going on when you look at a roller bearing. So I've given you sort of a cross section of a roller bearing here. So it's moving, it's rotating, it's orbiting, so it's moving towards us, and we're looking at it across the sort of we've dissected it like across the page, but due to the sort of contact angle of these spherical roller bearings, they're sort of tilted backwards. There are effectively different radii due to sort of curvature and this sort of tilt. And this means that when this roller rotates, different points along the surface are going to be moving at different speeds. So there's quite a complex sort of interplay of things going on, and there's also effects due to strain, so elastic deformation of material due to high loads, and this needs to be sort of fully actually considered to properly understand what's going on. And if because of this, even a very, very small sort of differences in speed across this sort of surface, here, this contact surface, if we get quite a very, very small slip, because the system is so highly loaded, we could get potentially very high frictional energies. So that's what my model went on to investigate. And so we're now moving into a microslip regime, and what I did is I used sort of Carter's strip theory to solve the microslip equation. And sorry to throw an equation in here, but basically this looks at a point on the contact patch, and it says that the slip speed is just a function of this is a term due to geometry. This is sort of a spin speed, so we're neglecting that as we're not assuming spin in the system, and these are sort of strain terms. And just sort of quite simply, all it does is the Carter strip theory sort of splits the contact patch up into lots of little strips, and then it sort of establishes boundary conditions for each strip, and it says that it's a steady state system. The system's solved for equilibrium, and it solves the strain so that equilibrium is maintained over the entire sort of contact patch. So I implemented this method, and I found that it sort of gives you this. This is a classical sort of observation, really, that we get over a contact patch. We get these regions where there's no slip, and we also get regions where there's sort of constant slip and high slip, due to that sort of interplay of geometry and strain that I talked about. And then I sort of applied this preliminarily on a sort of test case spherical roller bearing, the same one I used in the previous macro slip model, and to have a look at sort of frictional energies. And we can see, due to that sort of contact angle I talked about, because the rollers are at that angle, we get sort of differences in where frictional energy is sort of concentrated. And to fully sort of conclude the study, it needs to be applied over a full range of operating conditions, and I'm yet to do that. So the next thing I then went on to, and as I mentioned, that microslip model is a steady state model. I've started looking at the sort of concluding parts of my PhD are looking at actually a transient microslip model. So if we look at a load profile, so these diagrams here, this indicates the load and the loading rates, so how quickly load is varying in time on a roller for like a sort of a static constant load. So for example, how a roller would experience a load in sort of a power plant wind turbine at a constant speed and a constant load, compared to sort of a time varying wind turbine load. And what you see is that the loads themselves are quite similar. So the red is sort of the wind turbine, the blue one is the power plant. The magnitudes of them are quite similar. However, when we actually look at the load rates, they're very, very different. So the load rates are much, much higher in the wind turbine. So the actual sort of time varying nature of it is significantly different. And the large differences in these will not be detected by a steady state model. So we need to sort of determine if that's significant, and that was the next work that I was concluding. This is just a sort of a table of showing how those roller loads and loading rates vary over sort of different wind conditions, and we can see that the loading rates in get much higher, in sort of sometimes an order of magnitude or so higher. This could be due to effects such as load reversal events, where basically a gust of wind lifts the shaft up and drops it. So we're getting sudden large peak accelerations, and this is just sort of a graph of that figure. This is sort of a logarithmic scale, by the way. So we're seeing much higher loading rates when the wind speed increases, and we're getting more chaotic conditions. So basically, how to investigate that is to extend this steady state microslip conditions to include this time varying term, and that's something I've been investigating, but I'm going to just sort of skip over. And the final sort of bit of work I've got to do over the last month or two. So I've been away on industrial replacement whilst my rig is still being implemented. The remaining steps for that are implementing the sort of hydraulic control and a few remaining instrumentation issues with the ultrasound. And again, the idea of this is sort of it should support my theoretical component of my work. So these are sort of the remaining tasks really of my project, and then I'm finished. So sort of test the steady state microslip model over the full range of operating conditions, just like I did for the macroslip one. Finish the transient microslip model where it considers the load rates and not everything in sort of steady state, and then again test it over the full range of operating conditions and compare results from all three models and the strengths and weaknesses of each. Experimentally, I've got to link up the ultrasound sensors for film thickness measurements on that triaxial rig. I then have to test those looping loads I've talked about on the test bearing, and then analyze torque and film thickness against the loading patterns and compare the results. That is all. I hope I've not run over. Thank you.
You didn't run over, Elisha. That was perfect timing.
Grand.
So, Dice, you could go back onto the slide pack.
Can you see that?
So one thing, while Di's sorting that out, one thing I forgot to mention is that we have two sorts of projects in the PTRH. We have full PhD projects, which are 3.5, 4 years, and you just heard from about Elisha's. We've also got the flexibility to do much shorter pilot study type feasibility projects. And the one that I'll be presenting in a second or two is one of those. So it's a project which is Gary Nicholas's project. He did it when he was a researcher. He'd already got his PhD, did it as a research assistant, and about bolt tightness.
Sorry, unfortunately, my PowerPoint's just crashed. I'm going to reload.
I could run it off mine if it's going to.
If you could do, actually, yeah, that could be easier. Thank you.
Is that sharing now? Okay.
Yeah, you can see your screen. Yeah.
Can you see the screen with the right slide?
Yeah. It's
So
the project presentation slide. Is that right?
That's it. Yeah. And this is Gary Nicholas's project. So, and he's on holiday this week, so he couldn't be here. That's a misprint. It should say Gary Nicholas. So this is really his project. I'm presenting on his behalf.
No, we're still seeing I think your last slide with the list of projects.
Oh, what's happened there? I think. Have I got the right one now?
There we go. Yeah, perfect. Thanks.
That's it.
Full screen. Perfect. Thank you.
So this is all about bolt tightness and whether we can detect it using accelerometers. So the motivation is that bolted connections are widely used in wind turbine drivetrains, prone to self-loosening, which is obviously a safety hazard and potential for misalignment. There's a high number of bolted connections, as you'd imagine, in a wind turbine, and manual inspection is very time-consuming. So this is all about passive sensing using accelerometers, which could potentially allow for a quicker detection of bolts. So the aim of the project was to develop a method of detecting wind turbine drivetrain bolt loosening using vibration data. And there are 4 objectives: building a test protocol on rigs in the lab, identifying the best sorts of sensors and configurations, and carrying out some testing, and then building signal processing algorithms, which we can use to analyze and process the data from experiments. And then the 4th objective, which isn't finished, is about using those algorithms on Levermouth data from the Levermouth turbine provided by OREC, which is really kind of an aspirational objective rather than a delivered one. So the methodology, well, there's 2 methodologies that Gary looked at. The first one is essentially measuring the resonant frequency of the structure. So as bolts loosen, it changes the stiffness, and that then the stiffness reduces, and that then reduces the resonant frequency. So measuring the resonant frequency and looking from Fourier transform data of accelerometer measurements to identify the resonant frequencies and to pull out as these changed. Now I'm not going to talk about this because it didn't really work. We found that it was very hard to detect which bolt. You could detect changes in the stiffness structure and the resonant frequency, but very hard to determine which bolt was loosened. So I won't be presenting any data from that. You could certainly detect when a bolt was loosened, but not which one. So that the method that I'll show today is a linear regression method, and what Gary did is created this thing called a characteristic damage parameter. So essentially, the way that the model works is you look at the accelerometer data during a period of tight, when the bolt is tight, and you build a regression model to predict what that accelerometer data would look like going forward into the future. And then you compare that with what you actually get from your measurements, and you produce a residual, a difference between the two. And this graph, this equation in the bottom right hand side is the standard deviation of that residual measurement for a loosened case divided by the standard deviation of that residual measurement for a case where there is no loosened bolt. So there's more on that in the paper that I'll give you a reference to later on, but that's essentially how the method works. You're predicting the accelerometer signal and comparing that with a modeled accelerometer signal to see how far off you are. So the next slide. Oh, I'm doing this. I'm sorry, I'm controlling it now. Next slide, Rob. So the test setup was conducted on an electrodynamic shaker. So we built a test plate. You can see it on the top right-hand side there, with a series of bolts, and then shook the whole thing with electromagnetic shaker. And we tried different test procedures on how we loosened these bolts. And here are the accelerometers, one on the actual shaker to look at the input signal, and one on the actual, I think we've got a couple on the actual plates there to look at the output signals. And we sequentially loosened bolts from top to bottom, and then loosened inner bolts and outer bolts, and then looked at reducing the torque of a center bolt until it's fully loosened to see which of those three cases we could detect using the measurements. We used two kinds of accelerometers, two frequencies, a 2 kilohertz one and a 50 kilohertz accelerometer, to see the effect of the sampling rate on the results. So here's some data from the higher frequency measurement, 50 kilohertz, and you can see that this damage prediction parameter DF, you can see it very successfully predicts no bolts failing and the effect of increasing the number of bolts which have been fully loosened from top to bottom, 4, 3, 2, 1, and then no bolts. And you can see that predicts it very well. And then what have I done? And then the other sequence was to remove the inner left and the right bolts were loosened, followed by the outer left and right, and subsequently the center bolt's torque was reduced. So it's 3 separate cases in there, and we could look at how this damage parameter was changed by the loosening. We could predict that as well. These are measurements at 50 kilohertz. Sampling at a lower frequency, 2 kilohertz, still possible to detect the damage parameter DF. It's still sensitive to the number of loosened bolts, but less sensitive to the variation in bolt torque. So maybe dropping the bolt torque down didn't significantly change the vibrational properties of this, so you could pick it up at these lower frequencies. Generally, the resonant frequency of this structure is in about this region. It's in the kilohertz region. So these sensors should be fast enough to be able to predict, to be able to sample that. But in this instance, it didn't quite get the reduction in torque on the bolts here, although it could predict when the bolt was fully loosened. And then the kind of the aspirational goal is what can we do with recorded data. So this is not really results, it's a challenge. This is data supplied by ORIC, which is vibration sensors from the already on the turbine, and you can see that there's two sets of data and two very different sets of data, and we haven't yet, but the frequency is too low. This is only sampled at 1 hertz, and so we couldn't predict at this low frequency the sorts of measurements. But the trick is now to see if we can find alternative methods to either sample this data or use higher frequency sampled data. So in conclusion, Gary tried resonant frequency methods and regression methods to detect the loosening of the bolt of the bolt joints. So the regression methods were able to function well regardless of the sampling frequency of the accelerometer. So we were able to do it at 50 hertz and 2 kilohertz. The resonant frequency methods could detect loosening of bolts, but not which bolt was loose. So a sampling frequency of 2 kilohertz was also sufficient to allow bolt joint loosening. The minimum sampling frequencies are dependent on the resonant frequency of the structure, and typically, as I said, around about this 0.3 to 2 hertz for wind turbines. The most successful algorithm was the auto regression methods, and these can be used to provide an indication of bolt tightness, with the latter method requiring higher computational power. So I'll stop there. This is really Gary's work, but if you want to read more about it, then that paper there contains the full details of what he did. So that's the end of me for the moment. You'll hear from me a bit later on, and then the next person, I think it's Emily up next. So I shall stop. So I shall stop sharing and hand over to Emily.
Yep. Can you all hear me and see that?
We currently have the presenter view. If you can flip it, please.
It's okay, cool.
Display settings, I think, at the top.
The top, the
Which is display settings.
those settings. Is that better?
Perfect, thank you. Yeah.
Yeah, cool. Sorry about that. So yeah, I'm Emily. I'm a PhD student at the University of Sheffield in the PTRH hub, and I'm doing my PhD on the facing materials of hydrodynamic main bearings in the wind turbine drivetrain. And I'm in my second year of my PhD. So just an introduction, as you saw on Elijah's presentation, wind turbines usually use these rolling element bearings to support the non-torque loads experienced at the rotor, but research and industry is now going towards using these tilt pad journal bearings instead in these for the main bearing, but they're usually used in high-speed applications. The behavior in low-speed applications isn't really widely studied so much, so what we're doing here. So why are we going to be using these tilting pad journal bearings in a wind turbine? So the issue with wind turbines is they're getting bigger, they're getting more powerful, so they're getting bigger. So the main bearing size is getting bigger. So you then have a diameter limit when you transport them by road, and you can't split apart these rolling element bearings like you can with these tilting pad journal bearings. So that's a major advantage. You can also replace the pads in situ, and you can use smaller vessels to transport the individual parts, and all of this goes to reduce the downtime. So wind turbines operate at low speeds, as I said before, and they have a high number of start-stops. We have these start-stops due to the cut-in and the cut-out of the wind turbine. So as we decrease the speed during start-stop and just general operation idling, we go from hydrodynamic lubrication through to mixed and boundary lubrication. And so we're going to get asperity contact, and we're going to get wear and potential catastrophic failure due to this. So we need to protect the bearing from wear, and we do that by using a lining material, which would sit here on the tilting pad. But the issue with testing, like conducting tribological testing on this material layer, is that we don't know the testing conditions, like we don't know the loading or the lubrication conditions. So therefore, I have a need to study SCADA data, so data collected from wind turbines to understand start-stops. I have a need to do two models, so a simple beam support model and an analytical model to model the pressures. So first of all, just go through me quantifying start-stops. So I studied 1 year of data, SCADA data from a 3 megawatt wind turbine, and I got some results in the algorithms. You can see the shutdown events over the year. You can see me correlating the shutdown events to the wind speed. So I found that there were approximately 300 shutdown events over the year, and I related the shutdown events to the wind speed. So we can say that these are independent of our wind turbine size. The shutdowns, I recorded the length of the shutdowns as well, which are about 16 minutes, but our data is only taken every 10 minutes, so we have to take that with a bit of a pinch of salt. So moving on to my simple beam support model. So wind loading was generated on bladed software and a 1.5 megawatt wind turbine to get the rotor loads, and then these were translated across using a simple beam support model of the drivetrain, as you can see there, to resolve the forces in the Y and the Z directions. And as you can see, we got some loading here. This is the loading we got on the tilting pad journal bearing. And as you can see, this is pretty complex, and this is due to the wind field having spatially coherent turbulence. It's also due to it having a shear profile due to the friction of the ground, tower blocking of the actual tower of the individual wind turbines, and the wake of it being part of a wind farm as well causes all that. So we got some results. So we got, I found the mean pressure on the pads of the different wind loadings, and you can see the first bearing, the drivetrain, it's about 7 megapascals at maximum, but it increases with an increase in wind speed. We found the maximum about 10 megapascals, and the second bearing, the drivetrain is much lower, has much lower load, as you probably expect. So just about 4 megapascals as a mean value and 6 megapascals as an average value. And just to make you aware, this assumes that one pad is loaded at a time. So we also found the frequency of the pad loading. We found that 2 pads were definitely more loaded than the others, and just to say that in the future we're going to update this with this spring model. So looking at the analytical model, we built an analytical model, which is important so we can do our tribological lab testing, and that's just a little schematic of what we did. So essentially we first had to find a pressure, and we do this by using the Reynolds equation, and we wanted to use an assumption on the Reynolds equation because normally it's in 2 dimensions. So what we do is use a combination of the short bearing and the long bearing assumption, which is called a correction factor method. And we have to adapt this method to be used for tilting pad journal bearings because, as you can see there, the boundary conditions are different. Looking at those bottom 2 images, and the film thickness equation is different. So we went ahead and found the infinitely long bearing assumption, and we're using a Summerfield substitution, which is used for a standard case, as you can see here, where the film thickness is just there. But the issue we have with using the substitution with the film thickness for a tilting pad journal bearing is that we have to consider all these different factors involved in the film thickness, so journal movement, pad tilt, and pad curvature. So we just did a bunch of maths so we could write the film thickness equation for a tilting pad journal bearing as the same way as for a standard journal bearing, and therefore we can use the Summerfield substitution to perform this analytical integration for the infinitely long bearing case. And when we did that, we got a pretty close match between the numerical and the analytical models. And you can see the film thickness there across the pad too. And next we did a moment convergence to find the tilt. Did that there, you can see. And then we applied the correction factor across the whole pad to get a pressure distribution. So the future work is to complete the force convergence of this model, and then we should have a much better idea of what the pressure is doing on the pad, or what the pressure field is doing. So moving on to the testing. So what kind of materials do we need? So we need to withstand high amounts of boundary emulsification during the loaded start-stops, and we need to withstand moderate loads. We need to have a low coefficient of friction due to starting the wind turbine, and it needs to be temperature resistant because we think the temperature oil supply is going to be shared with the gearbox. so it's going to be high temperature. So looking at the materials, type of materials we're going to test. So we've bought polymers, obviously, as an obvious choice. Filter peak is currently being investigated by industry, but we think it might be an over-engineered design, and it's also really expensive. So we're looking at a few cheaper alternatives. We're also testing on bearing bronze and babbitt. So how are we testing? So we're using the modelled loads and the predicted start-stops, and we're using those values to build a test matrix to then use on a conformal block on pin setup, as you can see there, conformal block representing the pad and the steel pin representing the shaft. So this is the T67, and that's what we're using to test. It's pneumatically loaded from the back, loads transferred to the front using the loading arms. You can see there, that's our test specimen with the conformal block and our rotating steel pin. So the testing we've completed so far. So what we wanted to do based off studies was to do some 0 to 2000 RPM start stops with 10-minute length start stops, 1000 cycles and 20 megapascal loads, but probably go higher too. But so far we've just conducted some 310-minute start stops on peak, and we haven't seen anywhere. We've gone from 0 to 800 RPM and 20 megapascals. And you can see just to the right here, a little video of our start stops for the peak. And we've also conducted 41 60-second 0 to 400 RPM start stops on bronze, and we saw 0.2% mass loss. The reason why we haven't done what we've quite wanted to yet was because we are limited due to our temperature control. So we can't keep temperatures low enough and accurate enough to 72 degrees to do longer tests, but now we should have that under control. So doing tests is pretty imminent on some more materials and these same materials too. So to conclude, did a SCADA data study to quantify the frequency and length of start stops, but we want to apply that to bigger and more data sets to kind of verify the results we've got. We've done a simple beam support model, but we need to share the load better between pads, and we also need to consider the elasticity of the materials. We conducted a summerfield substitution for an infinitely long bearing and successfully implemented that for a tilting pad journal bearing. We applied the correction factor using that summerfield substitution to find the pressure approximation, and we've partially implemented that and got a pressure profile. And we've also conducted some initial start-stop tests, and we found that peak is more wear resistant under predicted conditions compared to bronze, but we want to optimize the test time using SCADA data. We want to optimize the test load by completion of the models, and we want to test on more materials. So yeah, that's everything from me. So pass it on now.
And yes, and I'll take over now. The last time you'll hear from me, and
would you like me to try and share this time? No.
I think I've got it now. I think I've got it, Dies.
Yeah,
Can people see that okay?
Yeah, just go to full mode.
Presenter mode.
Yeah.
So again, this is work that's been conducted by Gary Nicholas, and also another of my RAs called Joanju. Joanju's left now, and as I said, Gary's on holiday, so I'll be presenting on their behalf. And this is all about oil film sensors for hydrodynamic bearings. You kind of heard this already from Emily, but there's a lot of industry interest in replacing bearings in the wind turbine. Most of the bearings in wind turbine powertrain are rolling element type bearings, and as they get larger, that becomes more complex. And there's a lot of interest in replacing rolling bearings with hydrodynamic type bearings, particularly tilting pad bearings, like you see in this image down here. And of course, the oil film, and as Emily's just most clearly pointed out, the oil film formation here is really important. And because the wind loading is highly transient, the oil film formation is also likely to be transient. So it'd be very nice to know what that was in the bearing during its operation. And that's what this project's all about. My group does a lot of work building sensors, ultrasonic sensors, to measure oil film thickness non-invasively, so you don't have to put it inside the oil film. It basically works on a reflection principle, like you can see here. If you put an ultrasonic sensor on top of the bearing, the bearing raceway and send a sound wave through, ultrasound reflects back at interfaces. And the more acoustically different the materials are, the more that's reflected back. So we have this thing called a reflection coefficient, R, which depends on the difference in density and speed of sound between these two materials. So for example, if you have steel against steel, perfectly bonded, all the sound wave would pass through. If you've got steel against air, all the sound wave would be reflected back. And of course, what we've got is a steel against, we've got an oil film. So we've got a reflection at this oil film here. So what you would get is you'd get one reflection at the front of the oil film and one reflection at the back of the oil film. But actually, because the oil film is so, and if the oil film was really thick, you could detect those two reflections in space, and you could work out from the speed of sound in oil, you could work out the thickness of the oil film. But of course, those oil films are really thin. So what you get actually is just one reflection from this interface. So what we do is we don't separate it out in space. We separate it out in the frequency domain. So this picture on the right-hand side is a reflection when there's no oil film present, just air. And then everything reflects back, and you get a signal that looks a bit like this. You'd see an excitation pulse reflected from the sensor interface. You'd see a first reflection from the air interface, and then a second bounce as the wave came back and bounced again, first, second, third, and so on. And then if you then put an oil film in the way, then you get this red signal. Some of that ultrasound has passed through the oil film into the second bit of metal, and so you get a slightly lower signal. So this first reflection, blue is when it was against air, we call that a reference. Red is when it's against an oil film, and we call that the measurement signal. So we take that signal, the first bounce, and we Fourier track, well, there it is. We zoom in on it, and you can see it's slightly smaller because some of the sound wave has passed through the oil film. And the thinner the oil film, the less sound will pass through. If it's a thick oil film, this red line will be lower. We Fourier transform that, there we go. And then we measure the reflection coefficient, which is the amplitude of the red one divided by the amplitude of the blue one. And we put that in this equation. And you can read all about this in the papers that I've been writing over the past, well, over many years. But we can measure that reflection coefficient, the proportion of the sound wave reflected. And we can do some fairly simple analysis to get the oil film thickness out of that. The kind of equipment that you need these piezoelectric transducers, something like this. We usually build our own from piezoelectric material, stick it, bond it on the bearing back face, send it through and receive it by the same piezo. So that the voltage is converted into a mechanical wave that travels through the material, bounces back and converted back into a voltage again. And that's what this pulsar does. It generates these short duration voltage signals, and then a digitizer receives them and converts them back into a digital signal, which we process with LabVIEW. This is the basics of the way of measuring a pulsar, a receiver, a digitizer, and a laptop to process it all. There's various different ways of doing this. We've got different sets of equipment, some more sophisticated than others, and some very simple. But that's in its essence what it does. We've done this on lots of different kinds of hydrodynamic bearings. Of all sorts of different kinds. I'll be talking about the tilting pad case that Emily was just presenting. So we've got, as I see it, we've got two options here. One option is to put it on the pad, and that's this up. That's the simpler option. The pad is obviously stationary, it tilts, but we put the sensor either on the back of the pad or somehow in the pad. Here's an example here where we've drilled a small hole in there and recessed the sensors in there just to protect them, but it could be on the back face of the pad. Here are little sensors, and then we measure continuously in that one location. So that's all well and good. That's a nice simple application. The problem is these pads, as Emily pointed out, are likely to have a facing material, a polymer, to withstand if it was metal facing like white metal, it wouldn't be any problem. But these polymers and then an interlayer, they have their multiple reflections. They're going to reflect back from here, reflect back from here, and reflect back from here. So the signals start to get a bit messy. And so, whoops, I'm coming back to that in a minute. So you don't get a nice clear reflection. You get a reflection which contains lots of other information as well. And it becomes a little bit tricky to separate out the reflection caused by just the oil film, that's the green one, from reflections from other things like the steel copper reflection here. So this is going to depend very much on the construction of the pad, whether this is going to work. If these layers are thin, it's going to be successful. If they're thick, it's probably not. Here's a sort of a simulation of the process, and you can see why. You can see why as you get all these multiple reflections bouncing back from the interlayer, from the polymer layer, they all superimpose and you get a complicated signal. So at the moment, we're not working on this. We have done some work on this, but we've paused that. And we're working on another approach to doing this, which is going from the shaft side. So what we do now is we put a sensor in the shaft, which means a hollow shaft, somehow getting the wires out, running it through a slip rings, and then recording as the sensor passes into the oil film thickness and out again. And that has the advantage. Well, first of all, the signals are cleaner because you don't have all those interlayers to worry about. And secondly, you've got a continual reference. So we can measure out here as the sensor is here when there's no oil film, and we can pass into the oil film and back out again. So we can get a full 2D sweep of the oil film thickness as it passes around the circumference. So our signals, as you can see here, are much cleaner. And this is the current focus. We've not done this yet on a wind turbine application, but we've done it on other kinds of journal bearings. So here's an example where we've done it not in a tilting pad bearing, but a journal bearing. We've measured the circumference, the oil film thickness around the circumference of a conventional journal bearing, not a tilting pad one. So some benchtop investigations to see how this is going to work with the typical bearing materials that we're going to see, as Emily mentioned, PEEK. So we've done some benchtop investigations, putting shims. It's really quite hard to generate an oil film in the lab. You know, how do you generate a 5 micron, 10 micron oil film in the lab to test it? And it's quite tricky. And the way we do it, which is not perfect, is we use these very thin shims of metal, which we squash between two blocks of flat material. We put a drop of oil in there, squash it down, generally put a weight on top. Here it's put in a press here, so with a load cell to squeeze it down nice and tight. And we hope that our oil film thickness is about 5 microns if we use 5 micron shims, or 10 microns if we use 10 micron shims, etc. One of the purposes of this experiment was to try out what different frequencies to use. The higher the frequency, the thinner the oil films you can measure. And what do we need for these actually relatively thick oil films? So we started out with steel, oil, steel against steel with an oil film in the middle. And at these these oil films are actually relatively thick in the tribological terms, and so actually you want to have fairly low frequency, and at low frequencies these are our measured reflection coefficient against our theoretical reflection coefficient. When you get to higher frequencies, then more of it gets reflected back because it's not quite so sensitive, so it becomes harder to take the measurements. So and if you convert that to film thickness using that equation that I showed you on the third or fourth slide, you get very good agreement for these low frequency transducers. So that's easy, that's quite successful. If we use the right kind of frequency, 2 megahertz, we've got a good stable signal, and we can get good measurements of oil film thickness around about, well, here we go. When the shim was 5, we measured between 5 and 6. When the shim was 10, we measured quite accurately 10. When the shim was 15, we measured quite accurately 15. We reckoned it was plus or minus about between for about half a micron for 2 megahertz. It gets less accurate when you use the higher frequencies, because the higher frequencies are more sensitive to the thinner films. Now it's steel oil PEEK. So now what we're doing is not steel oil steel, but the more realistic case of steel oil PEEK. Does it behave as well? Well, it's not quite as easy now, because PEEK has got a different acoustic impedance to, that's that term Z, a different impedance than steel, so it becomes a little bit tricky to measure it, but you can still do it. We get good agreement across. Here's our reflection coefficient measurements here for a 2 megahertz, a 5 megahertz, and a 10 megahertz sensor. But we tend to get an offset in the 2 megahertz region. So I'll just show you something in a minute. So possibly why that's the case. So when we convert that to oil film thickness, it's not quite as clean as steel oil peak. It's not quite as clean, but you can still get measurements in the right sort of region. Here we've used much more different. We did many more different shim thicknesses as well. We tried. Tend to work a bit better at higher frequencies, in fact. One of the problems is generating the oil film. So we had a lot of problems getting. Well, first of all, our peak surfaces weren't particularly flat. Here's our measurement of our peak surfaces, and you can see here that it's quite a way off flat. And when it's 2 microns off flat, and you're only trying to measure 5 microns, this is actually a significant error in the measurement. We have tried grinding this, but really can't get it so much better. And compressing it also deforms it as well. So even though this is quite low pressures when we're compressing it in the test rig, it deforms the surface. So there's an uncertainty about what the oil film thickness actually is in reality. Right. So conclusions. We've investigated and identified suitable sensors for monitoring wind turbine sliding bearings in both metal, but also polymer coated bearings. Monitoring from the pad side, the feasibility depends on the structure of the pad. Different pads have got different layered structures, and some will be successful and some won't. The shaft side gives more reliable results, regardless of the pad, but needs a rotating sensor, more complicated to install. And we've conducted benchtop trials on steel, and steel peak. And the accuracy for those methods, for steel, very high. For steel peak, depends a bit on the frequency of the transducers. And I think that's me. Yes, thanks. So I'll stop there, and I think I'll hand over, and I will now hand over to Di, who'll wrap up the session.
Brilliant. Thanks very much. Yeah. So we had a small slot in now for Q&A. Firstly, thank you to the speakers, all keeping brilliantly to time. If you have any questions now, put them in the chat. We have a couple to start with. First one was from, both from Ankit. The first one about the presentations. So I just need to check with all the presenters today that we're happy to share the slides, and then they will be uploaded onto our YouTube channel along with the videos. So they should be able to be found there as soon as everything's been posted. And then secondly, there was a question for Rob, just following the last presentation. What is the pad thickness which deforms?
Yeah, so I don't recall the actual thickness of the peak layer in there. I think the metal isn't going to deform very much, but the peak layer on top, it depends on who's making it, but probably about 1 millimeter or so. And it only has to deflect by a couple of microns, and that's large compared with your, relatively large compared with your oil film thickness. So it's quite sensitive to that. Was that the question you were asking, Ankit?
Had nothing back, so I'll assume.
I presume so.
Yes.
Thanks.
If there are any other questions, put them in quickly. I'll give you a minute before we close out the session. Doesn't look like we have anything coming in, so I'll just close this out now.